Good afternoon. My name is Michael Kaisel. These are my partners, JP Sorongo and Mike Menos. We're going to be giving you a presentation on formula race engine development. As far as what we're going to be speaking about in this presentation, we're going to be giving you an overview of what Formula SAE is exactly, and how we divide our vehicle into different systems. Specifically, the engine package, or the engine system, is what we've dedicated our senior design project to. In this engine package, we have designed and manufactured intake, cooling, fuel, and exhaust systems. We're also going to give you a cost breakdown of our project, as well as some engineering standards and global design considerations. So what exactly is Formula SAE? Formula SAE is a collegiate competition with two main categories. There's a static event and a dynamic event. Inside static events, there are two competitions, a design competition and a cost competition. In dynamic events, there's an autocross and an endurance competition. Here at FIU, we separate our Formula SAE team into 7 main systems: drivetrain, chassis, suspension, electrical, aerodynamics, ergonomics, and finally the engine system, which is what we've dedicated our senior design project to. What you see in front of you is the finalized design of the 2015 Formula SAE engine package. Starting from the right, this is the radiator assembled with fan shroud and fan cooling system. This is the exhaust. This is the Yamaha YFZ450 engine, which we use for our engine package. This is the fuel system, and this here in the center in red is our main concern, our main design considerations, which my partner JP is going to talk more closely about.
Thank you, Mike. So this is the intake system as modeled in the CAD. The intake system consists of 4 main components: the throttle body restrictor, the intake plenum, the interchangeable runner, and the fuel injection module. The throttle body restrictor is a converging diverging nozzle with a bell mouth inlet and is required in order to comply with competition rules. The intake plenum acts as a reservoir for the engine during transient operating conditions. The interchangeable runner allows us to increase or decrease that plenum size in order to fine-tune the engine for our performance requirements. And the fuel injection module is to support the fuel injector and the fuel rail. It is designed such that the fuel injector is oriented in a 25-degree inception angle with 1.4 inches from the intake valve. It is also designed to engage the stock intake boot for optimal sealing conditions. So we measured the choke flow or maximum airflow of our restrictor on a flow bench and compared that to our maximum expected airflow for our engine, and found that the choke flow was much higher on the restrictor than what we expect our engine to draw. We then looked at the size of our intake system in terms of volume and studied how that impacted engine performance. We then developed a simple way to change the size of that volume in order to tune the engine for our specifications. And now my partner Mike Menos is going to discuss our computer simulation activity.
Okay, to get a better idea of how our changes affected the engine, we utilize Ricardo Wave, a 1D engine and gas dynamics simulation tool that allows us to see how the intakes affect the entire system. What Ricardo Wave does is essentially treats the entire engine as a series of ducts and orifices, giving the orifices, like the throttle orifice that you see here, a K value in the modified Bernoulli equation. All pertinent engine information and geometry were inserted to software to get an accurate engine model. For example, what you see here is in the orange circle represents the cylinder, and the engine is a single cylinder, has 5 valves, 3 intake, 2 exhaust, and we also modeled the intake and exhaust systems. After we achieved some baseline numbers comparable to the factory engine, we then applied the restrictor to the factory engine just before the throttle orifice. And what we did was applied some orifice values to the restrictor to let us see what kind of restrictions the restrictor was applying to the engine. When we got numbers that we deemed valuable from the restricted simulation, we then applied our plenum model to our initial plenum model to the restricted engine. What we did was we applied the plenum just before the throttle orifice and after the restrictor, the final restrictor orifice. This curved section here represents the same curved section in the CAD models. And what we did is we got the same data that we got the data from Ricardo Wave and inserted it into ANSYS to get flow simulation. We then improved our initial CAD model with by increasing the radius of curvature here and also reducing the length of that curve by eliminating this section here. These charts represent the horsepower and mass or torque curves and mass airflow curves over the entire engine range. The first one represents the unrestricted engine. And as you can see, the restricted engine has a dramatic decrease in both mass airflow and torque. And when we applied our plenum with a 4-inch runner, you can see that we recovered some of that mass airflow and torque. This graph shows the percentage of mass flow difference between the different plenum models and the unrestricted engine. As you can see, there's about a 25 to 30% decrease in mass flow by percentage from 7,000 to 11,000 RPM. And with our modified plenums, you can see that we've reduced that, or we've increased the mass flows in the same range by about 15%. And finally, for the graphs, we have a horsepower over RPM curve. As you can see, with each increase in plenum volume, there is an increase in horsepower. And we've almost achieved the same peak horsepower as the stock engine. Now my partner JP is going to talk about some validation.
So our evaluation activity involved measuring the air intake pressure and the throttle position using a MIDAC 2-channel oscilloscope / data acquisition system. In this way, we can measure available engine airflow with respect to driver input or demand. The results of that data is these two graphs here. On the left, you have a graph of a non-restricted engine, stock the way it comes from factory. On the right, you have the engine with the restrictor and our intake system with a 4-inch runner. The black line is the pressure from the voltage from the pressure sensor, and the red line is the voltage from the throttle position sensor. The red spike that you see there is representative of us physically opening the throttle and letting it shut, what we refer to as a snap throttle. What you'll notice is that with the non-restricted engine, the pressure voltage is much higher at idle than the restricted engine, and right at the spike you see an increase in pressure, then you see a pressure drop. That indicates that the engine RPM is very, very high still, and it's drawing a lot of air. As that throttle closes, that air is no longer available, so the pressure drops momentarily. Once the RPMs come down, then the system pressure recovers. We also looked at a qualitative aspect of our design and developed a simple scoring sheet to look at basic drivability parameters. The intake system was manufactured using additive manufacturing processes. The intake plenum was made using selective laser sintering, while the fuel injection module was made using fusion deposition modeling techniques. And now Mike is going to discuss the cooling system.
Going on to other engine subsystems, the cooling system is what you see in front of you, the finalized CAD model of the cooling system. More specifically, we printed the radiator fan shroud using ABS plastic, which successfully cleared a 1-inch gap given by the fluid inlet of the radiator. We chose this radiator because it was the closest to the factory YFZ 450 radiator for the engine. We were also successful in reducing heat transfer due to conduction with neoprene rubber insulations for all 3 mounting points. And the fan shroud was then post-treated for any for sealing purposes of the plastic material. This is the finalized manufactured and assembled cooling system. As you can see, the neoprene on the mounting of the fan shroud, and it's successfully cleared this 1-inch gap dictated by the fluid inlet. Going on to the exhaust system, this is the finalized exhaust system as a CAD model. This is the finalized manufactured and implemented exhaust system. What we tried to do with this was basically keep it as factory as possible, with noise restrictions of SAE competition. Now we need to keep it under 110 decibels, which is why we chose this silencer as the end piece of the exhaust. As well, the packaging was chosen because of measurement restrictions. It had to be within 24 inches of the ground and 17 inches of the rear axle.
Here you see the fuel system that's modeled in CAD. Design features include a 50-degree ramp angle to match the driver's seat back angle, and an in-tank fuel pump for space saving, maximizing the space that we have on the chassis. The system capacity is 1.7 gallons. The Beachworks DW100 fuel pump was selected to meet the system pressure and system volume flow requirements, and the actual pressure is dialed in using an adjustable fuel pressure regulator. The tank was manufactured using lightweight 6061 aluminum and TIG welded, and pressure tested to 3 psi to ensure that there are no leaks. Now we'd like to show you a short clip of the engine running on the car with our systems installed.
So here we have a engine cost report. With respect to our project, the entire project cost about $1,400. So for the cost event of the design, for the cost event of the Formula SAE competition, the cost report team and the design team collaborated, and we projected the cost for the vehicle on a mass-produced scale. The total cost was about $13,400, while the engine package cost about 31% of that, which is $4,200. With respect to engineering standards, we were guided mostly by the Formula SAE rulebook, but with that being said, we utilized SAE 30R9 Gates fuel injection hose. We also used AISI standards for our 304 and 304L stainless steels, and we used SAE J429 rated fasteners. With respect to applying our vehicle or our engine package to other countries, not only did we utilize an adjustable intake panel, but we are utilizing an adjustable fuel and ignition management system. This allows us to apply, the ignition management system also the manual comes in multiple languages. This allows the end user to adjust fuel and ignition maps to account for different climate conditions and also different altitudes. With respect to future work, we've been provided dyno time at Creative Workshop, and there we'll monitor air-fuel ratio, and we're also going to do a track testing matrix to see how our engine performs in real conditions. Our sponsors, we had 4 main sponsors that provided us with manufacturing and financial support. The first one is Fiat Chrysler Automobiles. They gave us financial support. Toyota Technical Center actually did the manufacturing of our intake. Beachworks, as said before, provided the fuel pump, and also Boyd Welding supplied or manufactured the fuel tank to our specifications. With that being said, we'd like to note that we're the first team to actually develop an engine, consistently running engine package for Florida International University per the Formula SAE rulebook. And we'd like to conclude our presentation with a slide showing our timeline and important engine information. If you have any questions, we can answer them now.
You're the second.
What's that?
You're the second. There's another group one guy who built a car, but he didn't go to competition because he got a job at NASA. But anyways, he has a running gate.
Little details.
You're the second.
So you're the second.
Unofficially.
Consistently. Consistently. That we could go right now and it'll start.
So could he. But anyway, mind if I go first?
Go for it.
Fuel tank. Did you guys put any kind of foam in the fuel tank?
No, not in the fuel tank. It has a baffle.
You do have that, okay. Because that's something I've seen other teams do, is use foam as a baffling method. That's what kind of caught my attention.
No problems.
That's okay. You kind of answered some of my questions already with your future work. So,
So it does have a baffle to prevent the fuel sloshing. Also, the tank is sloped upward to match the upward slope of the chassis.
Right.
So all the fuel will tend to want to go towards the rear.
So, okay. And I understand you incorporated with the seat and all that, because that's difficult. Actually, you just had it just there. The baffle is that little bar in the bottom?
Yes. It's got three 1-inch diameter notches for the fuel
This
to
section
flow.
right here.
Okay. That kind of did catch my attention. Have you thought about maybe make it a little higher by putting holes in there?
As in the baffle plate taller.
Right.
So we only really, the tank is so small, we only really need the baffle to prevent sloshing when the fuel level is below half a tank.
Right. The reason I'm asking that is because in the competition itself, I mean, granted, you guys are not professional race car drivers, and they design the tracks, you only go at a certain speed. But the idea behind the competition is for the weekend warriors, like if you are on full bore with no restriction, you know. And when you do go through the turns, there's a certain G load, and a lot of times the reason for the baffle is all the fuel goes to one side of the tank and you run out of fuel.
Right.
Right. But if you just do it for the bottom part, that's fine and dandy, but I would still do it a little further, because when it's full, that's more momentum for that fuel to move around, and that's gonna throw in a turn. Remember, you're going full speed and your tire's at maximum grip, so anything could throw it off and you spin. So that's one more safety feature by having to go in a little higher. It's not something that's in the car that's gonna make it wanna shift a little. Okay, so that's the first thing that caught my attention. In doing your intake, you guys did a great job, by the way. That looks awesome. I've been to a couple competitions, and that's, you know, just like a bunch of the others. The runner, you have that where I guess you could have it in different sizes.
Correct.
Have you guys thought about playing with different sizes to see how it would affect the engine?
Yeah, that's part of our dyno testing.
Part of dyno testing, okay. Because that was gonna be my next question, have you tested the engine on a dyno? Okay. The numbers that you guys are coming up with, have you guys, besides using simulation software, have you guys, before you did simulations, kind of did it by hand, just so you have something to compare with?
Yeah, we created an Excel tool using some basic hand equations.
Okay.
And theoretical approach, and then compared that with Mike's simulation. They were very similar.
Okay, they were very similar. Okay. No, because that's, reason I say that, because when you go to competition, the design engine manager, you know, they're gonna ask you for those. And you're gonna say, oh yeah, we did this, you know, our calculator will say, you know, we were within specs. They're gonna ask you, okay, show us.
We have a design binder.
Right, take everything with you, you know, even your molds for your design or everything, because they wanna see everything.
That's a learning experience from another week.
Right,
Exactly. They want
right.
to take a look at everything.
They want to see everything. And in your cost report, when you did your cost report, did you incorporate every little detail as far as manufacturing, that intake, that fuel tank, that radiator, and the purchasing of all the hardware you purchased, did you include all that in there?
Yeah, that's including miscellaneous,
Miscellaneous, okay.
Hose clamps, tie straps,
every little thing.
Welding, did you include the welding in there?
the welder for the fuel tank.
The labor, yeah.
Okay, because they're gonna wanna see all that. And just so you'll know, if your numbers, let's say somebody donated the gas tank already manufactured, you guys built it. Let's say I come and say, here's a gas tank. And they gave it to you as a form of sponsorship, no cost. If you don't put the cost of the fuel tank in there, you know, and your fuel thing is lower than everybody else, if they're gonna say, great, everybody else cost them $4,000, you know, for the fuel tank, you know, system, and yours is $2,000. But that's unrealistic, so they're gonna add on the difference onto your design. You know, you say, well, that was donated. No, it doesn't work that way. You know, so, you guys did a really good job, and I applaud you guys for actually getting the car done, having a running car. My friend Carlos, he actually built the car, but then he went to NASA before he could go to competition, but he did get a running car. So I just had to say that. What's the hardest thing in designing your intake that you come across, and how would you change it?
I'll say data acquisition, getting a really good data acquisition system up and running. What we envisioned was a custom LabVIEW virtual instrument with mass airflow and RPM and a dyno and everything, and to be able to put all that together into a really solid engine, fully instrumented with all the data we could possibly want. That would have been the biggest challenge. We actually measured air pressure using a map sensor, but we also purchased a manifold, a mass airflow sensor.
Right.
And we made custom 3D printed housing for it. We put it on the end of the engine
Right.
to measure mass flow rate, and we had all sorts of trouble with that acquisition and getting that sensor calibrated and getting that to work. That was probably one of the biggest things that we had difficulty with. We had to scale down some of our validation activity due to time and the complexities of instrumentation.
That's really the main constraint, the
Right.
acquisition system, alignment, for example, we don't have it.
Right. Cool.
Why did you guys choose